guys, and welcome to today's video. Today we're going to go over parallel lines, proportional parts, breaking down a bit more about similar triangles and how parallel lines plays into that. So let's get started. All right, so this is a picture. I'm going to zoom in. I'll zoom out in a second. This is a picture we've seen before. We've seen this triangle before. We know these two triangles are similar. Okay, I'm looking at the small triangle and the big triangle. Many ways we can figure this out. First way is by realizing that angle A is in both triangles. And then because I have parallel lines, I have corresponding angles that are congruent. Okay, so we've seen this triangle before, and we know that it's congruent. Now, because they're congruent, not congruent, we know they're similar, Because they're similar, we can draw a few more conclusions, especially because those lines are parallel. And that's where you get the triangle proportionality theorem. If a line is parallel to one side of the triangle, then it divides the pieces into proportional lengths. Now, here's why this is special. Up until now, we have only been dealing with sides, so AB is a side of the small triangle. AE is a side of the small triangle. But if we wanted to do the big triangle, we had to look at AC, okay? AD. So small sides and big sides. Now, with this new theorem, we don't need to look at just the sides. Because we have parallel lines, I can say that the pieces are proportionate. Okay, this is unique. So I can say that A over C is proportionate to B over D. And this works. Now keep in mind, okay, these are pieces of the big triangle. So we're looking at the big triangle right now. We're not looking at the little triangle. So therefore A and C are pieces of the big triangle. B and D are pieces of the big triangle. Keep in mind that if you are trying to compare anything to a scale factor, okay, it is sides only. Okay, you should never involve little pieces like BC and ED. Never involve those with a scale factor, okay? Because those are pieces, and the scale factor is for sides only. Okay, let's do a problem. So here we go. We have a triangle. We're told we have parallel lines. Because we have parallel lines, we know that A, B, C, and D are going to be proportionate. So what this means is that 7.53, if we wanted to find PS, all we would have to do is set up the proportion. So I'm going to go just down my sides. I'm going to go x over 2.5 is equal to 7.5 over 3. And after we cross multiply, we get 3x is equal to 18.75. And then we divide both sides by 3, and we get x is equal to 6.25. We are allowing decimals because the problem has decimals. And there's your answer. Now, an alternative way, I can hear you through the screen, for those saying, Mrs. Boyer, I did it this way. An alternative way, instead of going down the sides, you can go across. All right, now what does that mean? Remember, things are proportionate as long as the cross products are the same. So if I want to say x over 7.5 is equal to 2.5 over 3, that's totally fine, because notice when I cross multiply, x is still being multiplied by 3, and 2.5 is still being multiplied by 7.5. So whether you did the red one or the blue one, your answer will be the same. Now, if we have a theorem, that means we also must and can have a converse. So, ta-da, here's converse. As always, the converse says the exact same thing, just backwards. So instead of being given parallel sides, therefore pieces are proportionate, we are being told that pieces are proportionate, therefore sides are parallel. Okay, so keep an eye on this when you're dealing with proofs especially. Okay, you can't bust out any of your alternate interior angles or corresponding angles theorems until you have parallel sides, or lines, I guess. So make sure that you are aware of that. Now, a common algebra style problem for the converse theorem would look like this. Notice the picture looks basically the same as the last problem, okay? The biggest difference is that we do not know those sides are parallel, so no conclusions can be drawn. However, we are given information about the pieces and the sides, so let's go with that. So I know that 3 is that one, 9 is this one, and here's some fun wording. We know that DG is 1/3 the length of GF. Okay, fun. If DG is 1/3 the length of GF, now what this means is if this piece right here, DG, is X, then this piece over here is 3X. So when we set this problem up, we will have X over 3X is equal to 3/9. Then we cross multiply and we have 9X is equal to 9X. Now, as odd as a statement as this is, keep in mind the question isn't asking what X is. The question is asking, are the lines parallel? And the lines are parallel if the pieces are proportionate. Pieces are proportionate if the cross products are identical. And 9x does in fact equal 9x. So yes, these pieces are proportionate, therefore, yes, the lines are parallel. Okay, so always keep in mind your question. Sometimes you will get weird ends to your problem like this, and that's fine. All right, now this one should be a little bit of a review. We've already talked about mid-segment, our triangle mid-segments, and then we talked about it again with trapezoid mid-segments. So here for round 3, let's go with mid-segments of a triangle. Now, as a reminder, a mid-segment of a triangle is when the segment intersects the midpoint of the two sides. So every triangle is going to have 3, like this picture is showing, because every triangle has 3 sides. Now, a couple facts about mid-segments. Number 1, part of the definition is they intersect the midpoints of the sides. Fact number 2 is that they are parallel to the base. And that's what this theorem off to the side is saying. If you have a mid-segment, then the mid-segment is parallel to the base. Okay, and then on top of being parallel to the base, it is also 1/2 of the base. So if this is X, then this whole, whoops, I got that backwards. If this is X, then this is going to be 1/2 of X. Okay, and we'll do a problem on the next slide, but key things to take away. Number 1, the base is parallel to the mid-segment. So that's going to bring back all of your corresponding angle theorems, as well as your alternate interior angle theorems, as well as your same side interior theorems. So there's a lot that's fair game when you have parallel lines. And then a pure mid-segment information type is that the mid-segment is 1/2 of the base. So let's practice. Here we go, we have a triangle. This triangle has a mid-segment, has 2 of them actually. So we need to find all the different measures. So first up, we need XZ. So this one right here, it is the mid-segment. It's opposite of RT. And since the mid-segment is 1/2 of the base, that means that XZ is going to be 1/2 of 13. Just like that. All right, the video is going to pause. See if you can find B. Okay, so how'd it go? Hopefully you got 14. ST is the full side. So if the mid-segment is half of the base, then the base is going to be double the mid-segment. Or you can just set it up as a brief little algebra equation and get rid of your fractions and solve for what ST is. Alrighty, last but not least, let's solve for the measure of angle RYX. Now, where is RYX? RYX is right here. Okay, now hopefully you see where this is going. If not, that's okay. Let's talk about it. Here's RT, here's XZ. The reason why I highlight those is because we know for a fact that those are parallel. The mid-segment is parallel to the base. Therefore, RYX is alternate interior to YXZ. Therefore, measure of RYX is equal to 124. So that's what I mean when I say that parallel lines bring in a lot of different theorems. Alternate interior angles is a favorite. Corresponding angles can sneak in there sometimes. And then same side interior angles is always going to be fair game. So just keep an eye out for those. All right, we got a few more theorems coming down on them though. Now, we've been talking about triangles with parallel lines in it, but what happens if we just erase the top of the triangle, erase the pointy part? Okay, I'll zoom in, show you what I'm talking about over here. So I have a triangle, I have a parallel line, all right, and then I'm just going to erase this top part. This picture right here is what we have on this slide. We already knew that that pieces were proportionate. So A over B is proportionate to C over D. We knew that within the context of a triangle. Now the Simon Says aspect of math is telling you that you don't need the hat, okay? You don't need a triangle. As long as you have parallel lines, okay, involving 3 or more of them, then the rule works the same. In all of these pieces, okay, let's say this is X, Y, Z, and W, all of these pieces are proportionate to each other, just like they were in our triangle. So X over Y is going to be proportionate to Z over W. And so you can solve problems like this. Okay, here's one. You see a lot actually of this particular theorem in art, especially brief art lesson. If you study Renaissance, okay, the Renaissance era will usually have either checkered floors, pillars, or a checkered ceiling, and that's to help with the parallel lines and the proportionality, and it's to help make things scaled down and look realistic. It's very unique portions. That's actually where you use this in real life, for those of you wondering. So if you're drawing a picture, you have a vanishing point in your background, and you're going to draw these transversals that go towards your vanishing point. You can kind of see the triangle, it's facing sideways. And then you have your parallel lines, which in this case are our picture frames that she's drawing, or the windows that she's drawing. Okay. Now this means that this segment right here, we know that AB is 8. We know that DC is 9. The YZ is 5. We need to know this piece right here. Because we have parallel lines being cut by transversals, all of these pieces are proportionate. So 8 over 9 is equal to X over 5. 40 is equal to 9x. And we're just going to leave this as a fraction. Technically speaking, I guess if you were drawing, you would actually go with the decimal. That way you could measure it out with a ruler. But we're not drawing this. So fractions come back to their superiority. Now, last theorem of the PowerPoint. Okay, so same picture. You have parallel lines. They are cut by transversals. We are now adding the fact that they are congruent parts. Okay, so think back to a few lessons ago when we talked about how if you have congruent shapes, those shapes will always be similar. Okay, congruent shapes have a scale factor of 1, so they're always going to be similar. What this means is, when applied to the picture that we were just looking at, here I go, looking at my picture. I have parallel lines. They are cut by transversals. One of them is congruent. Okay, these pieces over here. AB is congruent to BC. Because they are congruent, they have a scale factor of 1. Because they are proportionate to the other side, it means this side will also have a scale factor of 1. And that's all there is to it. Now, this does not mean that AB is going to be equal to FG. No. It just means that since one side is congruent, those pieces, then the other side's pieces are going to be congruent to each other. And here's a problem to show you how we do it. So in this instance, we know that we have congruent lines, or congruent pieces. So therefore, 3y plus 8 is going to be equal to 5y minus 7. Okay, you can solve the other side too first. I'm just going to solve this side because that's where my congruency markings were. 15 is equal to 2y. 15 over 2 equals y. Now, because I have congruent pieces over here, due to the theorem we just learned, we know that we will also have congruent pieces over there. So 6x minus 5 is equal to 4x plus 3. And then it's an easy solve. So this is going to be 2x is equal to 8. X is equal to 4. And there you have it. All right, that is the end of this lesson. Please let me know if you have any questions. Please, please, please make sure that you have copied down all of the examples. So if you do have questions, we can go over them when I see you next. And I will see you next time in class. Bye.